Okay, now I ask, what would the multiples of v1 and v2 be if we were to get the matrix, if we were to get the vector 1, 0? Not 1, 0 relative to the eigenvector basis or to the basis b, but 1, 0 actually down here in the plane. 1 unit here, 0 units. So the vector in the direction of the x-axis of magnitude 1. How are we going to find the multiples of these two eigenvectors, of these two basis vectors that give us this? Well, we say, okay, well, this is a multiple of your two vectors, v1 and v2. Okay? v1 is the first basis vector, v2 is the second basis vector. c1 v1 plus c2 v2, this just means that this is a multiple of v1 and v2, the two vectors that we have up here. Okay, and that translates into this equation. Okay, so once more, you see the phrase, okay, 1, 0 as a multiple of the basis vectors. Okay, if I call the basis vectors v1 and v2, then this expresses 1, 0 as a sum of multiples of the two basis vectors. I'm not sure I said sum of multiples a minute ago, but that's what I should have said, okay? And that's what the problem in your document says, okay? So this is a sum of multiples of these. That's exactly what this says, and this says exactly the same thing because I've just replaced v1 and v2 by their component form, by their column vectors. Okay, well, and it's obvious then, or should be, and if it isn't obvious, work it out and keep working it out until it becomes obvious that this is the same as this. Okay, this matrix equation is the same as this equation. Now, we've done this many times, but it's not a trivial thing. It takes a while to sink in. Okay, now, since saying that this vector is a sum of multiples of these two basis vectors is the same as this equation, we see that the two basis vectors appear as the columns in this matrix. So I can call this the matrix v1, v2, where we express v1 as a column, v2 as a column. Right there they are as columns. Okay, so v1 and v2 are right here and right here. Okay, now if I want to solve this equation, first thing to realize is this is your matrix of the matrix where your basis vectors form the columns. Okay, the column of basis vectors matrix. It's what connects representation here to what would be the representation over here in this basis, which would be the C1, C2. To solve for C1 and C2, we just have to find the inverse of this matrix. Now, if these are basis vectors, then they are linearly independent, and you understand that if these vectors are linearly independent, then you're going to be able to reduce this matrix, because that means your column space has rank, whatever the rank of your matrix is. So it means the row space has that rank, so it means the matrix reduces to the identity. So if this is a basis, you're guaranteed that this matrix is invertible, so that we can solve for C1, C2 just by inverting this matrix. Okay? Now, this matrix is a big deal. Okay? Let's see. Big deal matrices. I'll include this inverse and this column of basis vectors matrix, because these two matrices are what connect the representation according to this basis and the standard representation. Now, C1, C2 relative to this basis means what? Means C1 times the first plus C2 times the second basis vector. So that's just our representation with respect to B. And I could make a statement that well, let me get a better color here. Color I haven't used. So from this I can make the statement that 1, 0 is the same as C1, C2 relative to the basis B. Okay, that's what this result gives us. Okay, once more, big deal. Now over here, I just simply invert the matrix where the columns are the basis vectors. Okay, I inverted it, I checked it, and then I made some connections. Okay, now down here I said the same thing I said up here. So let me just circle that in blue. And just saying that C1, C2, B is the same vector as 1, 0, which is really just what I said here. But for emphasis, it doesn't hurt me to have said it twice. Okay, so I've inverted the V1, V2 matrix and checked. I checked by seeing that if I multiply this matrix by the vector 2, negative 6, which you recall is this vector here, okay? If I multiply the inverse matrix by that, I should get this vector relative to this basis. Okay, well, I'm sorry. I didn't say that right. Okay, if I multiply 2, negative 6, which is our R2 representation of this vector, and that should be a semicolon, I'm going to get the expression of this matrix, of this vector, relative to this basis. And that expression, if you understand what we've said so far, is just negative 2 times 0, 1 column, which is 0, negative 2. Meaning none of this, negative 2 of this. And negative 2 of this does give us this, doesn't it? Okay, well, that worked out. I multiplied this inverse matrix by the 2, negative 6. That's a representation of this vector with respect to the standard basis. And I got this, which is a representation with respect to the basis B. And I put a subscript B on it over here. Now, let me just kind of indicate also that T of 0, 1 is 0, negative 2 with respect to the basis B. This is the vector 0, negative 2. It's 0 of these minus 2 of these. This vector T of 1, 0 relative to B, that's a parenthesis, is equal to what? It's equal to, well, right there's our transformation, it's 3, 0 relative to B. This vector is 3 of these and 0 of these. Okay, now there's a real important connection that I'm going to make, and I'll review a little bit of this in a short video to follow.